think he said he was going to bring in a couple options to.
Okay. Another thing that we can do is to restart.
It's always a good option.
Yeah.
Oh.
Okay.
Okay. It's a good start.
Yeah.
No.
Now it has a refreshing thing. Interesting.
I'm just going to go step out and I'll meet Adam out there.
Mm-hmm.
You want to try to go next door, right?
We might have to. Adam's on his way, EMS guy. So if not, I'm gonna look up the schedule for next door and we'll see if.
Shall we restart?
You mean restart the computer?
Yeah.
I don't know. This must be the setting of this laptop. They have a refresh issue. Maybe
But it seems that it's not because it.
another
Try a different one?
Yeah, try a different.
Let's, but we need to make sure that that actually works. Yeah, it's tricky.
Well, I'm gonna have to leave at 12:55. Not that I don't
I'm
like
going to
anything.
take personal
Don't
offense.
take it personal.
I'm going to be tracking you.
Yeah, I have a meeting.
I'm going to time it.
Okay, all right, thank you.
No, thank you.
Okay.
This is your extended desktop.
The resolution
mirror.
is,
Okay, so we need to buy new adapters.
So some of the newer Macs have been having issues with adapters.
Okay.
We're seeing.
Oh, that's good to know. Is there?
Is this a newer
but
Mac?
this is not. No, this is not new.
Interesting. Okay.
Do you have a suggestion for what we should? Because
Well,
I think we usually just buy whatever's.
yeah, usually I'd say the Apple brand is usually
Get an Apple brand one. Okay.
probably more standard with the industry requirements and stuff like
Okay.
that.
We'll do that. We will. That's easy enough.
Okay.
Let's see. I want to wait until I open the PowerPoint, if
Yeah.
you don't mind.
That's fine.
The problem started when we opened the PowerPoint.
Adam is the man.
Thank
He
you.
is
You're welcome.
the right guy to get help.
Thank you.
Thanks, connection.
Yep. Perfect.
I may need to. Yeah, I'm connected to Wi-Fi. Okay, close it. Okay, good. Close. Everything seems to. And
Okay,
if
that's
there is
separate.
sound, yes.
Yeah.
And if there is sound to the videos, you know, if that appears, it's not critical, though.
That's nice up here. This HDMI.
Yeah, the volume control is here.
Yeah, we just might need to check the output. If there's, just jump in here for 1 second.
Sure.
System preferences. We will look for sound.
Please.
Oh, up.
Up, did I pass it?
Yep. Up.
There it is.
There you go.
Okay. Nope, I did not see it. All right. Yeah. So, extracts play through here. Looks correct. That should be correct. Yeah. So we can now close that.
And this. Okay. Yeah. You.
Yep.
Yeah.
Yep.
Okay,
Feeding to the room
wow.
speaker, so it should be good.
Yeah. Okay. Thank you.
What would you like me to do?
You can just leave it in the drawer and I'll get it later.
Yeah, let's get started. Now, thank you for coming for our IE. Welcome. We had some little bit of technical difficulty, but right now we fixed it. Yeah. And today we're very happy to have Professor Juan Wachs from the Adjunct School of Industrial and System Engineering And Professor Wachs also have affiliated appointment with the Biomedical Engineering, with the Department of Surgery at IU School of Medicine and the Johns Hopkins University. And Professor Wachs' research is on intelligent system and assistive technology. And he has received numerous research awards, include the Young Investigator Award from Air Force, Fulbright Scholar Award for U.S. Scholar, and ACM Distinguished Speaker Award. And let's welcome Professor Wachs to give us the talk.
Thank you very much. All right, so I'm going to talk today about how we can work with AI, use AI in a way that is not going to lead to what I called AI horror, right? When you look into medical applications, the last thing that you want is this type of horror when mistakes happen and things don't go as expected. All right, so let me start, here I guess, with a few words about my trajectory. I was born and raised in Argentina. I moved to Israel where I study all my studies and my family still lives there. Then I moved to Purdue in 2009. Those were old days where my group was quite large. And since I was at NSF, I have to reduce the size of the group to make it manageable. In 2020, I started a company called AI Medic, which is about using artificial intelligence for medical applications. I became a program director at NSF from 2021, and I finished my rotation this year in 2024. And I led the robotics program there, smart and connected health, and I help with the AI institutes. And as a hobby, I like climbing. Those are the Himalayas. Now, truth to be told, I didn't climb the Himalayas. There is actually, that is Kardungla, if you know, and there is actually a jeep that takes you all the way to the top. But you need to go down, right? And you can do that biking. So this is what I did. So it was still a lot of fun and so merry there. Okay. All right, let's talk about research. So these are the questions that I ponder about. If humans and machines are working together, and we work together, or at least we plan to work together in a lot of challenging problems, why we can't share our intelligence? Why this effort if you want to make machines and systems using AI solve all the problems if, after all, we are here and we can actually help, we can provide our side of intelligence? Why don't we think in terms of a collaborative intelligence, right? And how we can use that to strengthen systems. Now, in this idea of shared intelligence, I find particularly interesting solving problems where you deal with imperfect data, the imperfect world. It's very different than the control settings where you train your AI algorithms and your robots. And this is really what you find in the real world, right? The dynamic structures. So I'm going to talk about my work in autonomous robotics in a number of areas, and then I'm going to talk about the use of AI in HRI, in human-robot interaction. So in this, let me say a few words about this idea of shared intelligence. When you look into AI with humans in the loop, you have one axis, which is the human intelligence, and you want to maximize that as possible. And of course, there is a certain limit that at this level in our civilization, I can say that we have reached. And then you have the machine intelligence. And when I talk about machine intelligence, you can think of AI or embodied AI, which is really machines having all the strength of the computing power and the physical capabilities that the machines provide. And within these two axes, I look at shared intelligence as a combination of them, where your goal is try to achieve the maximum of both intelligences. And I'm going to put my work in the context of this, along this axis, to show you how the different ideas progress within solving these different challenges related to shared intelligence. So the first project that I want to talk about has to do with human and robot collaboration in a setting with very low human intelligence, if you want, and very low machine intelligence. And that specifically relates to the chest on Earth project. This is an old project, and I'm going to walk you through the whole development of this idea, but the idea was we look into how humans and robots collaborate in the operating room. We noticed that, for example, robots can be used in the operating room in the context of delivering surgical instruments, for example, to the surgeons, right? So robots can be used to replace, if you want, or help surgical technicians understand verbal signals and hand signals and deliver surgical instruments. Now, this was a robot. This was an industrial robot. You don't want to put an industrial robot in the OR. They're very fast, but they also can kill both the patient and the surgeon. But this is one interesting thing. It's most of the communication in the OR, and this is what we learned after observing a lot of surgeries, is actually implicit communication. It's not necessarily explicit as we imagine. If you want, surgical technicians and nurses, we call them mind readers because they know what surgeons need before the surgeons themselves know. And they can actually anticipate the needs, right? And this is an area that we found very interesting and challenging in collaboration in the operating room. So we wanted this robotic assistant that can deliver surgical instruments, but after solving the problem of computer vision, of identifying surgical instruments, making sure that the delivery is safe, combining different modalities to be able to understand behavior, we really focus on this interesting problem of turn-taking or anticipation, the need of the idea of being able to predict or anticipate the need of a surgeon. And that's an area in HRI, in human-robot interaction, called turn-taking, right? How we can actually predict those turns. And in order to solve this problem, we look into the inspiration of decision-making, of how we make decisions, and there we look into neural networks. Now, these are very similar to artificial neural networks that you know, but these are actually inspired, I would say, much stronger with real neural networks that we have in our brains. These are called spike timing neural networks, and the idea is that you have different type of neurons, really as happens in our brains, inhibitory and excitatory, and their behavior either blocks or encourages the transmission of spikes or signals, right? So you have connections between the neurons. You don't have hierarchies, and within the connections of neurons, you have delays that are really the delays in the synapses that affect the transmission of signals. But you also have weights, which is the strength which the neurons are connected, or the strength of the synapses. And neurons actually fire when you get when the critical mass, if you want, of signals arriving at the same time to the neuron, right? So the timing is what determines when the neurons are going to fire. So without getting too much into the details, and I'm glad to answer questions about this theory, but I'm going to try to summarize to the most important points of this work. What you can actually do with these neurons is you can change parameters that describe the behavior of these neurons or the physiology of the neurons, and therefore determine when they're going to trigger a response and how much time it takes them to recover, the transient, right? So you can play with the parameters and change the behavior of the neurons. And when you change the behavior of the neurons, what you actually do, de facto, is you change the response of group of neurons. So this can be used as a semi-supervised training algorithm where you can train those parameters to have the neurons respond as groups for similar patterns. So when patterns are similar, right, when patterns are observed and are similar, you get the same group of neurons responding. And when the groups are different, that denotes different patterns. So rather than looking at the individual neurons, we can actually come up with a nice way to represent this information in the form of distributions. And if we discretize that, we can use actually histograms. And we can use these histogram representations to capture these groups of neurons responding to a given signal. So we look into the responses of two characteristic behaviors, turn-taking and turn-giving. And these are examples of the groups that you see responding. the group of neurons that you see responding for turn keeping and turn giving. And you can see that there are some patterns that repeat. It's a very general idea, and you can see that overall there is some motifs that remain the same. So if we can use this feature or this knowledge representation form to describe these behaviors, we will be able to determine whether we have a turn-keeping or turn-giving event. So we use this knowledge representation technique to train the spiking neural network and to be able to recognize turn-taking and turn-giving events. And what we did is we compare our technique with other algorithms, which are machine learning algorithms for turn-taking, usually. And what you see is our algorithm is actually the red one, and all the others you see below. And the one that is yellowish is actually a human performer, a human assistant. And you see that we can predict really well when the turn-taking is going to happen early on in the turn. When we get 10%, 20%, 40%, we can predict with almost 85 accuracy when the turn-taking is going to take place. And as more evidence is accumulated, humans actually, the human assistant actually is better than the algorithm. We cannot beat the human there, right? So this is an interesting finding, and we published this in a number of venues, but I think that the most important lesson that we learn here is, it's not about beating the human, right? And not beating a professional surgical assistant or nurse. Maybe we should be thinking of finding ways to collaborate and strengthen the performance of both. And this is going to be one of the things that I'm going to talk later, how we solve that problem. Let's look into a different angle of this problem. And the different angle is what happens when you break the team and they are not collocated in the same place, how you can share intelligence in a situation where the agents are not collocated. So I'm going to take my axis of shared intelligence and I'm going to push towards the right side, okay, to increase the intelligence. And now what I'm going to do is I'm going to separate the agents and I'm going to mediate them through a robot. We'll see how this actually works. So the application that I want to showcase this idea is one in telemedicine. It's called telementoring and teleproctoring. So the idea of, what is the idea of telementoring? So the idea of telementoring is basically, assume that you are looking into a rural setting, an austere setting, field setting, could be the battlefield. You need certain expertise, surgical expertise that you don't have. What is the best way to deliver that knowledge? So you need a neurosurgeon that needs to treat a patient. You don't have a neurosurgeon. What is the best way to deliver that knowledge, right? Let me show you a short clip to kind of explain this concept.
Contact our mentor stateside.
Hello, this is Dr. Andrews. How can I help?
My patient was caught in an IED blast. His shin is swelling, and he seems to be in danger of developing compartment syndrome.
We need to do a fasciotomy. Don't worry, I'll walk you through everything.
He's ready for surgery.
Send me the data.
So let's move forward. But
We'll make 2 incisions. The lateral
the basic idea is you have this display, which was a tablet, and you mount on top of a patient, and you, using augmented reality, you deliver surgical knowledge, annotations from the experts to the remote setting. And in this way, once the annotations are aligned with the anatomy of the patient, right, and that involves some interesting problems in computer vision, the medic or the resident follows the instructions one by one, and in this way, the procedure is completed. Okay, so you have a remote setting where you have a medic or a resident, right? We were using at that point a tablet to augment the information, and then the mentors will be allocated in a Trauma 1 facility. For example, the University of Washington School of Medicine, I believe it's a Trauma 1 center. And you have experts collaborating on a visual representation of the patient, creating annotations. Those annotations are sent in the form of augmented reality to a tablet, and the medical resident can actually see them. So we created a prototype following these ideas, and we implemented that in the IU School of Medicine in the Atom class. It's a trauma class. I'm not going to get too much in details, but what they teach is they teach residents trauma treatment using porcine models, okay? So the idea was to use this system in fasciotomies. You see how it looks like. And the first design was really based on a small tablet for the expert and a tablet for the resident. So this was the first system or attempt that we had. And of course, we encounter a number of problems here. One of the problems is, as you can see, the tablet is in the way between the resident and the patient. Well, in this case, we have a porcine model, right? And surgeons are very good using their hands, but this is exactly blocking their hands, right? So they cannot do what they are good for. So we move into a different, another thing that we learn has to do with the design of the mentor display. So for example, you see the chief surgeon of trauma at IU, the way that he interacts with annotations is, using touch. Now you see a group, you have a team working on this representation. Look at the way that they interact with anatomy. They actually are laying surgical instruments on top. So we figure out that we need to come up with ways to recognize these instruments and represent that as a virtual annotations. Of course, we move away from the concept of the tablet. We move into the HoloLens. And this is a fasciotomy. And what we did is we had residents trained on fasciotomies. We have the expert creating the surgical annotations and those who are delivered to the resident, and the resident would follow the steps. Now, this is the thing. If you want to use this system in the field, you cannot really do that because you need an overhead camera, right? So this is still a control setting, and if you're thinking of a field setting, this is not going to be suitable. So what we thought is, why don't we use robots? We use drones or quadrotors to hover on top of the patient. We capture the views, deliver those views to the mentor, and allow them to create annotations. And that was something that worked well initially. As you can see, we have the drones hovering on top of the patients, capturing the views, delivering that to the experts, and the experts creating annotations that came in the form of augmented reality. But here's another problem. If this is going to really be used in a conflict situation, the drones are actually going to flag on the position of the casualties, right? And that is potentially risky. So we thought, why don't we use the camera that is on the HoloLens? Well, here's why you cannot really use the camera. It's because the camera is mounted on the head of the medic. The medic is looking everywhere. It's not just looking at the patient, right? So mentors are going to get motion sickness for all these motions. And we have to come up with ways to creating models, background models, permanent models, that would only capture changes in the anatomy of the patient when the anatomy is aligned with the model that we created. So this is what is called a stabilized view. We came up with a way to stabilize the view, and therefore we made this system be useful for the field. And of course, once you come up with a solution that seems viable, you want to try that. So we tried that on a simulated setting, on a military basis of special operations and medics. And let me show you a quick video of how that looked like for a crime.
It's time now for the Business of Health, brought to you by Hendricks Regional Health. A Purdue University researcher is taking the power of augmented reality to the battlefield. Business of Health reporter Kylie Valletta tells us how the project could save lives. Kylie.
Thank you, Gary. When soldiers are seriously wounded in battle and their injuries are beyond military medics' expertise, they often need to be airlifted or transported to the closest medical facility, typically taking several hours.
Let me show you how this looks when we apply this on simulation. This is the simulated setting with, simulated explosions, smoke, sound, and you had actually an instructor forcing the medic, screaming, shouting at the medic to perform this procedure on time, because there is basically the patient needs to be evacuated right away. So, we learned that this is something that can work relatively well if you do have the necessary communication infrastructure. Now, to be completely honest, the agent and the robot here, the agent, the robot, their intelligence, we're not really relying on their intelligence, right? There is not much intelligence there. So if you really want to come up with a solution where you have robots or agents that share the intelligence, or share in this case the cognition, you need to think of how these agents can help in the procedure. And we look into an example where we have a surgical procedure using a Da Vinci robot, where the task was to come up with an autonomous robot that will be able to share the cognition. And the way that this robot is going to help is in the task of suction, blood suction. So when you're operating, you have you have bleeding, and the bleeding accumulates, and you want the robot, or in this case, you have an assistant. Either currently the assistants are helping with the suction, or the main surgeon is still operating the robot to deal with the suction. But here you really want to rely on autonomy for this problem. So the idea was we mounted the Da Vinci with the necessary instruments to perform suction and the necessary intelligence to go and apply suction to the pulse, to the bleeding regions. And we thought, okay, rather than creating a complete autonomous system or semi-autonomous system, why don't we help the surgeon when he needs by looking at the cognitive load? And when we see that the cognitive load is too high, we're going to have the robot, the autonomy kick in and perform and assist by completing the procedure, right? So we say, okay, let's look at the EEG signals, okay, of the brain. Let's try to identify patterns of cognitive load. And the way that we do that is we ask the users to perform a very simple task of picking something, which is something simple. We measure cognitive load. And then we start creating this artificial bleeding. And we saw that the cognitive load was significantly higher. And you can actually see those patterns specifically in the delta and theta channels of the EEG. So a significant change in the responses, in the potentials, right? All right. Okay, good. Now, here's one challenge. In order to be able to detect these patterns, you need data. And we don't have data. And in fact, you don't need data only of 2 points that characterize low cognitive load and high cognitive load. You need really data over all the whole spectrum. You need to collect data of learning of a human is solving a problem of navigation, spatial navigation, okay, manipulation and navigation. That's interesting. And how we collect this data? So we thought, well, what is the task that you need to learn from scratch? And if you need to learn from scratch, you're going to fail in the beginning. Cognitive load is going to be as high as it can be, up to the point that you're good enough and actually you're able to solve this problem. So we thought that an interesting problem is biking. Now, biking is trivial. All of you can bike, right? But if I take a bike and I invert the controls and I let you bike, you're going to fall miserable. You're going to fall right away. Now, if I give you a good incentive after 2 weeks, and this is what you can do with your kids. You can offer Pokemon cards or something like that, and wait 2 weeks. They eventually master this. So this is an example of someone, for example, trying to drive this bike, someone that knows how to bike, okay? This is what happens when you invert the controls. And if you collect the information from the very beginning to the point that they get proficient with this bicycle, you actually can capture the whole spectrum of cognitive load for this individual, right? Now, of course, we want to do surgery. We don't want to bike. But it turns out that if you take a laparoscope or endoscope and you completely invert the controls, the situation is exactly the same. So you can capture these patterns and train a machine learning model to recognize those patterns and then intervene when necessary. And we created this system where now the autonomous agent is kicking in when the human needs it. So, right, this is the shared intelligence that I'm talking about. And by looking at the number of metrics, performance metrics in surgery, we saw that our system, almost in all the metrics, led to an improvement in performance in the blood section task. This is how it actually looks, if I can show. So the human is actually teleoperating the scissors and the forceps and is picking the needle and really here making a knot. And the autonomous system is actually is taking care of suctioning of the bleeding. And again, so we realized that this is the right way to go, this shared cognition or shared collaboration. So now we went back to the original project of telementoring, where really we rely on two humans, two humans, a mentor and a medic. And we said, can we use here AI and the shared intelligence concept to deliver, to improve the performance of the surgeries, right? So here we're looking at the highest level that we can achieve at this point, which is human and agent working together. And this is the Trauma Thompson project. So what is the Trauma Thompson? So you kick out now the mentor. You say, we're going to be deploying a telementoring system in a setting that there is no communications whatsoever. So there's no mentor, or the mentor is actually an AI agent, right? And what you want is the AI being able to figure out what's happening and provide instructions, and ideally using augmented reality, to the medic and tell the medic what to do. Of course, now again, you need a lot of data to train these systems. And the data that you have of surgeries is, most of the surgeries really in controlled settings or using the surgical intuitive Da Vinci. There is very little data of life-saving procedures in the field. So we thought, why don't we call the community? So we got inspired on the EPIC challenge. Have you heard about the EPIC challenge? EPIC challenge is try to use AI to help you cook. So they created this challenge where they ping people all around the world. They gave them GoPro cameras and they captured their activities while they were cooking in the kitchen. And the idea was to train an AI system that will help them cook whatever they're trying to cook, right? Will provide instructions. So can we do the same for surgery? That was the question. And it was a great idea, but a very bad performance in the sense that no one is going to let you collect data of people being trained on the field, right, when there are emergencies. So we said, okay, that's not going to work out. So why don't we collect the data and call the community to solve this problem by providing algorithms? And this is what we did. This was part of the MICAI 2023 challenge. Come up for 5 surgical procedures, and those are field procedures, come up with solutions in AI for activity recognition, activity anticipation, visual question answering, and procedure recognition, okay? So these are examples of the 5 procedures. And we came up with this challenge with these different tracks of action recognition, anticipation, task recognition, visual question answering. Let me show you how these look like. So the idea is, if you can anticipate what's going to happen, you can deliver that using natural language in the form of an instruction. So that is your mentor, right? But in order to do that, you need to be able to generalize really well. This is uncontrolled settings, and this is the more difficult part. You don't know what task is being performed. You only have information of what has been done so far. Okay, so it's an open set problem in machine learning, and it's very challenging. And this is what this is how it looks our system when it works well. Okay, so you're going to see the result.
Remove cap. Tightly strap. Twist windlass.
Ready?
Okay, so action recognition, again, deals with looking at a video, several frames before the current time and being able to tell what is happening in terms of the action. Action anticipation is be able to use the information that you have seen so far and stopping now tell what's going to happen in the future. Procedure recognition is the easiest one if you want. It's just a classification problem of activity recognition. When you have information about the type of activity. And the visual question answering is very interesting. This is where you can actually ask the agent things about the patient based on visual information. Some of the questions may look trivial, like, is the patient bleeding? Well, right, I mean, you will see blood, right? Now, there are some questions that are more interesting. Is the patient breathing? Is the patient conscious? And for this part of the challenge, we got inspiration from the DARPA triage challenge, where they wanted to use drones to deliver that to casualties and being able to see the patients and understand how to do triage. Part of the process is a dialogue of a drone and the patient, if the patient can actually talk or the casualty can talk. So this language problem or visual question answering problem is actually very interesting. So all this information needs to be annotated. We came up with a very simple way to annotate by using verbs and nouns like make incision, insert tube, okay? Very, very simplistic way. And this is how we annotated all the data set that we collected. And we went out to the challenge, and we threw that into a challenge, and we tried to see how well the community can do. And we were impressed to see that actually the best performer is actually quite low. But it's a difficult problem. This is not a traditional classification problem where the categories are known in advance, okay? So you see it's, the performers are actually in light blue, okay? The best that they did was between 30 to 40%, about 35%. And I'm going to show the results for the other tracks, but what we learned from here is we actually met with the performers that submitting winning results, and we tried to discuss with them what are the right strategies to solve this problem. And after the challenge, we have been working in this problem, I think it's 1 year now, and as you see right now, our best performance is over 67% about, okay? So we're doing much better. Action anticipation is not as good, it's a little bit lower, it's up to 60%. Visual question answering, the best results is around over 70%. And it's not such, I think, it can be a more interesting problem if we add more interesting questions as well. But this is where we are with this project, right? And I think that there is a lot of room here for improvement. Let me talk about the best performer. Our algorithm at this point is based on transformers, or vision transformers. The idea of transformers you probably are familiar with is basically a technology or an algorithmic solution that replaces traditional neural networks or deep neural networks and is inspired on the field of visual language processing, right? The way that you solve this is trying to, rather than memorizing patterns of words, you focus on the concept of attention. So where you find correlations or connections between different words, right? The same idea has been applied now in the recent years to the area of computer vision with really nice results. And what is interesting in this version 2 is that rather than working with patches of the images, you can actually work on self-attention models that reduce the resolution every time more and more. By the time that you work with the smallest resolution, in a way, your decision, rather than based on local information, is based on, if you want, a global representation of what's going on in the scene. Okay, the last thing that I'm going to say, well, that's a few things, is just-in-time procedures. So this is interesting. So we said, okay, if we can recognize activity, we can recognize this actions, what happens when we start playing with it? What happens if we have a MacGyver? We throw a MacGyver, for the people that know MacGyver, do a tourniquet, but you don't have really the elements to do a tourniquet, right? You only have a t-shirt, right? I mean, this is the thing. But why this is interesting? This is interesting because in locations where there are low resources, you may not really have the surgical or the tools that you need to be able to perform these procedures. So come up with how well we can recognize, we can throw this to our algorithm and recognize these improvised. Now, doctors don't like the word improvised procedures. They said just-in-time procedures. There's nothing improvised in what we do. Okay, so just-in-time procedures, tourniquets using belts or T-shirts, to autonomy, using, for example, a screwdriver, needle crank, using, for example, a needle to release air, and so on and so forth. And as expected, the results are bad, okay, as expected. Now, that's a good opportunity to work on it, right? So right now, our best performer is 12% for action recognition and 8.42 for anticipation. And in top 5 accuracy, we're doing better, but it's really a challenging problem. So in order to solve this, what we are doing now, I'm going to tell you a little bit about what we are doing now. We are using knowledge graphs or task graph, where you can actually take these procedures and represent them as graphs. And the nodes represent nouns and verbs. So for the actions, you can connect nouns and verbs together, and you can generate a whole graph for every trial or every procedure, right? Now, what is interesting in these graphs is that you may actually have direction, but you also may have cycles. So they are not traditional non-cycle graph, right? But you can still use algorithms of data science, right, to represent this knowledge and to do a number of operations on these graphs. One of the things that we want to do is to be able to recognize these improvised procedures, or want to be able to recognize mistakes and proficiency, right? So, of course, we have the graph. You can take the graph and represent that using a matrix, matrices, adjacencies matrix. You can, if you have cycles, you can use an ordinal matrix together. You can have those matrices. And by vectorizing these matrices, you can actually have a way to represent this data in an efficient way. Now, we also use PCA to reduce the dimensionality. And now you can see, for example, for several trials, by looking at the confusion metrics or the distances between this vector representation, you can see really the similarity of the trials among the same type of procedures and different types. And what you see on the right are prototypes. Now, the last slide, if you want, is the most interesting part. Is now we can actually recognize mistakes, but we also can recognize shortcuts, or we call them shortcuts now because the improvised procedures that we're looking at are mostly shortcuts, but we are going to explore now other types. And by looking at the clustering distribution of these points, using 2 different representations of the graph, we are able to detect both mistakes and shortcuts. So this is very useful for the just-in-time. Last but not least, we're also tracking right now the hands and detecting objects to try to understand the proficiency and the expertise of the medics, and also see if we can detect confusion by if you want, the erratic behavior of the hand movements. All right, I'm going to summarize what we did. So this was the question that I started with about shared intelligence, how we can come up with methods and techniques in shared intelligence to improve performance. And what we learned is that, again, it's not about beating the human. It's about working with the human. So coming up with useful solutions is thinking how we find efficient and I would say, techniques that allows the integration of both human and intelligence and machine intelligence. The other thing is you need to consider socio-technical factors in this integration, which are not straightforward, and they are difficult to optimize because first you need to model them, right? And these social technical factors, for example, are sometimes you want to recognize activity recognition. Well, the activity that you expect to see is not necessarily the activity that the practitioners are going to do. If someone needs to save a life, and what they have is a belt to do a tourniquet, they're going to use the belt. So you need to understand, come up with ways to modeling this, for example, improvised techniques. And this is where we use, for example, knowledge graphs, right? Last but not least, a lot of AI is based on training, reinforcement learning approaches that are applied to simulations, using, for example, ISEC, CHIM, and others. And the problem is when those are deployed, you have what is called the sim to real gap, or what I call the robotic horror from the first slide, right? So how to solve that problem? There's not an easy solution, but one way to solve the problem is to have the human in the loop, in the reinforcement, if you want, the reinforcement process. So you can have elements of the real application during the training and not wait until the systems are optimized, so you deploy them and you see actually that they don't work because they have been trained in pure simulation. With that, I'm going to conclude my talk. Thank you so much for the invitation.
Thank you, Professor Wachs, for this very interesting talk. So we have a few minutes for questions.
Okay, first of all, great talks, really insightful. I learned a lot, especially on the potential of shared cognition. And well, with this whole shared cognition, and it's a difficult problem, but assuming that you manage to solve it somehow, what do you think, how do you think it would improve the problem in human autonomy control? Because I think there's an issue of, which tasks to be assigned for human, which tasks to be assigned from robot, but with this shared cognition, how do you think it would improve the approach to solve such problems? I hope
I have more questions than answers. Can I ask a question? I know that this is not commonly accepted. No, but you see, there are problems. I want to agree with you in a way that, first of all, I'm not going to come up with a solution that is going to be one glove fits all. There are infinity solutions, but there is, in my opinion, if you want, a right track and the wrong track, and the right track is try to see how we can work together with the systems rather for us to be nuanced and or you know, more an obstacle to the optimization of AI. There are problems, social technical problems that are different to model, difficult to model. And some of the problems, for example, are dealing with trust. Right? I haven't talked about trust, but I know that you guys here, a lot of you work on the trust. You need to trust the system. If you're talking about autonomous driving, as you said, right, you need to be able to trust, and you need to be able to measure trust. So I talk how we can share cognition to alleviate cognitive load, how we share cognition to alleviate, to improve trust, right? And those are problems that there is not one solution. There are several solutions, and I think that all of them are worthwhile exploring. I would say that I don't know if we can actually get to the point that you can rely completely on a system and say, now work, perform surgery, or take me to my destination and fall asleep. I think that the human interaction is an important aspect here.
Thank you, Juan, for a really interesting talk, and I really enjoyed a number of these projects. They're really quite advancing some of these methodologies. So this is a question dealing with implementation of the technology. So you showed us like the confusion matrix, and things are getting better in terms of recognition, but there's still errors. And I'm just wondering, what do you think about the actual implementation of this technology versus the cost of an error during a surgical procedure, and that trade-off. I suspect that in the military there are different values that come into play versus what might actually happen with a with a civilian surgical procedure, and it's more than just trust. And I'm just wondering if you have some insight into
this
that.
This is for a long conversation. I mean, there's so many interesting points that I have opinions about. I would say a few things, and I'm not sure that I have answers to all. First of all, when you look at the just-in-time with 30% or 12% accuracy, that, to put it mildly, is not performing poor. It's performing terrible. Okay, so there is much more work that needs to be done. And what is the threshold for which we're going to allow people to really use the system? I think that there is a lot of practice in industry that we can learn from. One of the things that I learned is when you look at Surgical Intuitive and which projects they fund, and I'm talking about fundamental science funding, they didn't touch for years autonomy. They would be interested in human factors. They would fund human factors, but they wouldn't touch autonomy. And what was the reason? I had interesting conversations. Well, no hospital is going to pay for that because the cost of the claims are going to be so high that we are going to be broken, they're going to be broken. No one wants to get into this. Now, interesting that you can do that, but no one is going to buy it. So now, they are now recently funding projects in semi-autonomy. So parts of the procedures are done in autonomous manner where you have a surgeon observing. So there is a transition in the cultural acceptance of the society of what we're willing to do. Look, if I tell you 30 years ago, would you step into a car that is going to drive or have some autonomous features that you can actually take your hands out of the wheel? Would you go on that car? You would say no, because, you are aware of all the crashes and accidents occurring without that. Why you're going to add? Well, it's happening. So I do think that, it's possible to work with the technology and these problems, fundamental scientific problems, to get to the point where, if the trust is increased, the overall performance is going to be increased, and those systems are going to be actually being allowed to be used in practice. But there is a long way. We are not there.
I'll just reiterate what everyone else has said, that it was a really great talk, so thank you. I'm curious about the cognitive workload that you were measuring with the EEG, if you foresee those kind of workload levels, like the processes that you're looking at, if you're going to be using those EEGs levels to map and kind of see if the tasks are consistent enough to label different parts of the task as like high versus low workload, or if you're planning on using that information and that you would need like real-time measures kind of on top of that, because obviously you can't be using EEG out in operations. And then also just your thoughts on other physio signals that could be taken from the operator and used to improve the shared cognition.
So this is interesting. I do think that we're going to get to the point that EEG signals are going to probably near infrared. Information is going to be extracted from surgeons, and how it's going to happen, well, no one is going to allow you to stick things on their head, but surgeons operating on the Da Vinci, they need to sit, and they need to put their chin on top of a holder. So there are going to be ways that in a way that is non-intrusive, you will be able to measure EEG signals. You definitely can measure other things right now. You can measure sweat. You can measure how much stress are you putting when you sit, and that's also an indication of a cognitive load or stress. So there is a number of ways that you can come up with these metrics that are done in a way that they're going to be more accepted. Now, you can do that also to measure different facets of the surgery, and also to do that with respect to any surgery. And you can induce more cognitive load. So for example, we show that when we pump more blood, this artificial blood, and some users actually didn't know what they're actually operating. They came to the experiment, we didn't say that this is a simulation. These simulations are very realistic. Some of them got really stressed. When you get to pump a lot of blood and they see bleeding everywhere, you see their cognitive load, peaking. And that's interesting because you can use that information to actually provide assistance. So there are a lot of ways of combining this information and other physiological signals as well, right?
Yeah, I have a question regarding the last work. I know right now using the video sequence to recognize human activity is very popular. A lot of people work on it. I know in manufacturing, people do that, try to identify operators' activity. And the task graph idea to look at the sequence of actions is also a popular idea in this field. So in your work, what are the special challenge like using this graph task? Yeah.
Sure.
Yeah.
I will get to answer. So in the field of activity recognition, what I want to emphasize is that this is an open set problem. Yeah. So let me reiterate that. We want to use the system for procedures that were never learned. I want the AI being able to assist. That means there are certain patterns of actions that we believe remain the same regardless of the procedures, the same way that when you are cooking, you may pour oil, I don't know, in your pan, whether you are doing fries or eggs or whatever, right? Okay. So this is what is called an open set problem. It's an area of few shot learning, and those are areas, solutions to those problems are very difficult. I would say that efficient solutions for this type of problems are in the infancy. So we can definitely contribute knowledge there. In terms of knowledge graphs, yes, not graph exists. The use of using, the idea of using graph theory to solve a variety of problems related to task performance exists. But I would say that I would definitely not say that the work in task graph or graph theory is over or done in any way. I do think that, for example, our work is using neurosymbolic representation. What we publish, in fact, appears in the last, which is using the idea of task graphs. Where is that? Here, I think. It's using the idea of task graph together with transformers to improve the overall performance of the system. So the combination, and there is convolutional neural network, neural graphs. We want to use that with do a similar, if you want, breakthrough with transformers using graph theory applied to transformers output, which is what we have done here. All those are in really infant, I would say, areas of research that are really in the infancy, and they are not really good results right now in the community for this.
Okay, thank you. Do we have other question? So if not, thank you for joining the curriculum. Yeah, thank you.
By the way, if you want to know if there is a good community trying to solve a problem, come up with a challenge and offer money. No, seriously, and you based on the submissions that you get, you actually can understand how well people are dealing with that. So it's really good. Anyway, thank you. Thank you very much. Thank you. Okay.
Catherine Woodruff. I'm one of the students.
Nice meeting you. Nice meeting you.
I was just curious if you had heard of the DARPA program called In the Moment.
No, In the Moment.
Yeah.
Oh, who is the program director? You know?
Audra Roberts, I think, or Audrey Roberts, I think is her name.
Yes, it's in I2O directorate.
Yes. Yeah.
I don't know. I know some of the directions, but I don't know this particular program.
Yeah,
It's new?
I think it started a year and a half ago. It might be wrapping up soon, actually. But it's.
What is the name? Wait a minute. I need to write down this. I want to find out where.
They're looking at decision making in MASH casualty.
Oh, it's not the triage pro.
Yes,
It's the triage. Yes.
One, yeah.
Yes, I know the one.
Okay.
They were using the drones and stuff.
Yeah,
yes.
yeah.
And in fact, I know that one of the faculty actually here wrote a paper with someone.
Oh, really?
And that I think that I need to look. I have the paper here. Okay. In fact, yes. Oh.
Okay,
yes.
I was just curious.
So yes, it's relevant,
I
right?
was gonna say,
Well, we submitted an entry. We were invited to a full proposal, and we didn't get it. I was working at NSF. There is a problem of government submitting, even that I'm not government, but there is no really way to explain to them. It's a problem to have government funding government. So and I will never know what was the reason that we didn't get it. But see, one of the things that we wanted to do is to come also with this solution of dialogue. So, because this is what medics do in order to triage, one of the things is they start asking questions.
Yeah.
So we can actually have the drones approach and ask questions and, get, and based on the responses, being able to know, how the patient is doing.
Yeah, very interesting. So that's what your talk made me think of, and I was like, if you weren't already kind of in on that.
It's the triage challenge.
Yes,
Okay, yeah. No, this is really related to that.
Yeah, it's okay.
Well, we wanted to do that work. We wanted to have it funded.
That's how my company, we submitted our
you have a company?
and we didn't get it, so either side. I feel you. Yeah, I work for Collins Aerospace.
Okay.
So,
Where are they located here?
They're based in Cedar Rapids. I just work remotely and then do PhD part-time. So.
Wow.
Yeah. So,
Well, good for you.
Yeah, thank you. So it was really
Pleasure
nice
meeting you, okay? Take care.
Thanks.
Okay, let's see, where's that?
Yeah,
Here. Right. Thank you, Shiyu, for your help. And,
so the next agenda is meet with our PhD student, have lunch.
It's always nice meeting with students. Okay. And it's always nice to have lunch.